Okay, we're going to be factoring a binomial. When you have a problem and it's just two terms, there's something you need to check for. You need to check and see if it's a difference of squares. So what is a difference of squares? Well, you ask yourself three things. Is the first term a perfect square? Is the second term a perfect square? And is this a subtraction problem? Okay, so let's look at what is a perfect square. So a perfect square is that means when you take the square root of a number, it's a whole number. So the square root of a number gives you a whole number. Okay, so let's look at some examples. Well, let's just start with the easiest one. 2 times 2 equals 4, right? So the square root of 4, oh, I read the answer. So the square root of 4 is 2. The square root of 4 is a whole number. So 4, the number 4 is a perfect square. Okay, 3 times 3 is 9, right? Okay, let's look at the number 9. Is 9 a perfect square? Well, when you take the square root of 9, do you get a whole number? Yes, so 9 is a perfect square. So I think you get the idea, but that also works when you have variables. So let's look at variables. X times x is x squared, right? All right, so let's look at x squared. Is x squared a perfect square? Well, when you take the square root of x squared, you get x. So yes, x squared is a perfect square. All right, just to make this a little bigger, x squared times x squared is x to the 4th. Okay, so we look at x to the 4th. Is x to the 4th a perfect square? Well, the square root of x to the 4th is x squared. So yes, it's a perfect square. If we had x to the 3rd, can you multiply anything times itself to get x to the 3rd? No. X squared times x squared is x to the 4th, and x times x is x squared. But there is nothing you can multiply times itself to get x to the 3rd. So if you were to take the square root of x to the 3rd, the answer would actually be x times the square root of x. That is not, it still has a square root in the answer, so this is not a perfect square. X to the 3rd is not. All right, and then one more I want to look at. If we had x to the 9th, okay, is there anything you can multiply together, something times itself, to get x to the 9th? There is not. See, x to the 3rd times x to the 3rd is x to the 6th. So you can take the square root of x to the 6th, and you'll get x to the 3rd. So x to the 6th is a perfect square. But x to the 9th, there is nothing that you can multiply times itself. You could do x to the 4th times x to the 5th and get x to the 9th, but this isn't the same thing. So you have to be able to multiply something times itself to get a perfect square, so that whenever you take the square root of it, it will just be an even answer. There won't be any square root left in the answer. Okay, so be really careful whenever you're doing these. We won't have one like this in our problems, but I just wanted you to be aware. Okay, so now that you know what a perfect square looks like, we can look at how to do these problems. I did that whole video where it wasn't showing. There, I'm not going back to do it. Oh, great. Okay, so let me give you a second to record it. So x squared is a perfect square because when you take the square root of x squared, you get x. X to the fourth is a perfect square because when you take the square root of x to the fourth, you get x squared. X to the third is not a perfect square because you still have a square root in your answer. X to the sixth is a perfect square because x to the third times x to the third equals x to the sixth. But x to the ninth is not a perfect square because there is nothing you can multiply times itself to get x to the ninth. Because remember, when you multiply like bases, you add exponents. Okay, now that you have that copied, let's look at the first example. All right, so the first step you ask yourself is the first term a perfect square? Well, yes it is, because the square root of 81 equals 9. And then you ask yourself, is the last term a perfect square? The square root of x squared equals x, so yes, that is a perfect square also. Is it subtraction? Yes, it is subtraction, so you're good there. All right, so it is a difference of two things that were squared. So it's a difference of squares. So to be able to factor this, we are going to have two binomials when we factor it. The square root of the first term goes in the first spots. So the square root of 81 is 9, so that will go in the first spots. The square root of the second term goes in the last spot. So to fill in the last spot, we take the square root of x squared. The square root of x squared is x. That goes in the last spot. Okay? And then one binomial will be minus and one binomial will be plus. So we make one a minus and one a plus. And that is the simple way of factoring a difference of squares. Okay, let's check the next example. Okay, when I look at this, I think, okay, let me check for a greatest common factor first of all. Let me move my paper up. All right, is there a greatest common factor? Well, I can look at this. Again, you should be getting it good at picking out greatest common factors. I can see that both of these are divisible by 3. They're both divisible by 9, so I know there is a greatest common factor. So let me go ahead and write out the prime factors. And again, remember you do a factor tree to do that, but I'm going to do it in my head now. Okay, so this is 3 times 12, and 12 is the same thing as 3 times 4, and 4 is the same thing as 2 times 2. So you can get that same result doing a factor tree. And then n squared is n times n. Okay, for 27, there's a minus sign, so I'm going to put a -1. And then the 27 is 3 times 9, and 9 is the same thing as 3 times 3. And then we have m to the 4th. Okay, I can look at this and I see they both have 2 3s, and 3 times 3 is 9. So they have a common factor of 3, another common factor of 3. So the greatest thing they have in common, the greatest common factor, is a 9. When I take that out of the first term, I'm left with 4n squared. And then whenever I take that out of the second term, I'm left with a -3m to the 4th. All right, so we took out the greatest common factor. Now we look at it. Is the first term a perfect square? Yes, I can take the square root of 4 and I can take the square root of n squared. But when we look at the second term, is the last term a perfect square? No, I cannot take the square root of 3. So this is not, can't take the square root of 3. Okay, so this is not a difference of squares. So you cannot factor it using a difference of squares, so we're done. The only thing we could do was take out a greatest common factor. Okay, so whenever you cannot take a square root of one of the terms, that means it's not a perfect square. So that means it's not a difference of squares. All right, let's do the third example together. So we ask ourselves, is this a perfect square? Well, I can take the square root of 16, that's 4. X to the 4th. What times itself gives me x to the 4th? Well, it's x squared times x squared equals x to the 4th. Okay, so that is a perfect square. Is the last term a perfect square? Well, can you take the square root of 1? Yes. 1 times 1 equals 1. So the 1 is a perfect square. Is this subtraction? Yes, it is. All right, so we have a difference of squares. That means we can go ahead and write our binomials. The square root of the first term will go in the first spots. So the square root of 16, and then the square root of x to the 4th, and that will go in the first spots. And then the square root of the second term will go in the last spots. So the square root of 1, square root of 1, okay? And then one of the binomials will be a minus, and one of the binomials will be a plus. All right, so we factored this difference of squares. Now, most of you would stop here, but you have to be really careful and check. See this binomial? There's a plus sign, so that is not a difference of squares. But if we look at this binomial, we can actually take the square root of 4, and we could take the square root of x squared, and we can take the square root of the 1, and it's a minus sign. So this factor is a difference of squares, and this factor can be factored even further. The square root of the first term goes in the first spots. The square root of the last term goes in the last spots. 1 is a plus, 1 is a minus. All right, so we factored that. Okay, the first factor, we just bring that down and write it with our answer. All right, so sometimes you factor your difference of squares, and then one of those can be factored even further. So it's kind of like a factor tree again. We factored it into 2 binomials, and then this binomial can be factored even further into these 2 binomials. Okay, we cannot take the square root of 2x, so we're done. All right, that's how you do difference of squares.